Often called Earth's sister planet or twin, Venus captivates us with its intriguing similarities and stark contrasts to our own world. With a diameter of about 7,520 miles, it is only slightly smaller than Earth, and both planets share a composition rich in rock and metal. Positioned as the second planet from the Sun, Venus orbits at an average distance of approximately 67 million miles, creating a celestial neighborhood that has piqued our curiosity for centuries. However, beneath its mesmerizing exterior lies a brutal environment that defies our expectations. While Earth is a vibrant world with a plethora of life forms and a climate that supports diverse ecosystems, Venus presents a harsh landscape characterized by extreme temperatures, crushing atmospheric pressure, and an atmosphere that is toxic to human life. Today, we will delve into the thick clouds of Venus, revealing the secrets of its turbulent atmosphere, geological features, and its tumultuous past. Venus and Earth share a striking resemblance in several ways, including size, density, and geological features. Both planets are classified as terrestrial, meaning they possess solid, rocky surfaces. Venus's mass is about 81.5% that of Earth's, and the two planets are composed of similar materials, primarily silicate rock and metals. Their densities are also comparable, suggesting that they share a similar internal structure. The geological landscapes of Venus and Earth reveal fascinating parallels. Both planets feature mountains, valleys, and volcanic activity. Venus is home to vast plains, large volcanic structures, and impact craters, painting a picture of a dynamic geological history. However, the critical question remains: how did two planets so alike evolve into such drastically different environments? To uncover the answer, we must examine the role of their atmospheres, geological processes, and their positions relative to the Sun. The climate of Venus is one of the most extreme in our solar system. Its atmosphere, predominantly composed of carbon dioxide, approximately 96.5%, along with clouds of sulfuric acid, creates a runaway greenhouse effect that has driven surface temperatures to staggering heights. The average temperature on Venus is around 900 degrees Fahrenheit, 475 degrees Celsius, making it the hottest planet in our solar system, even more so than Mercury, which is closer to the Sun. This intense heat results from the atmosphere's remarkable ability to trap thermal radiation. Sunlight penetrates the thick clouds and warms the surface, but the heat struggles to escape. This phenomenon creates a perpetual cycle of heating that leads to the planet's current scorching conditions. Additionally, the presence of sulfuric acid clouds not only contributes to the greenhouse effect, but also results in a highly corrosive environment, making surface exploration incredibly challenging. Adding to its unwelcoming nature, the atmospheric pressure on Venus is approximately 92 times greater than that of Earth, equivalent to being nearly a mile underwater. Such pressure poses significant challenges for any spacecraft sent to study the planet. Most missions have only been able to survive for short durations before succumbing to the harsh conditions. The weather on Venus is characterized by thick, swirling clouds of sulfuric acid that create a constant shroud over the surface. These clouds not only obscure our view of the planet, but also contribute to extreme weather patterns. The atmosphere is marked by strong winds that can reach speeds of up to 200 miles per hour, 322 kilometers per hour, at the upper cloud layers, while the surface remains relatively calm. This discrepancy leads to interesting weather dynamics, including potential lightning activity within the clouds, though direct observations are still limited. In addition, The thick clouds create a greenhouse effect that leads to a consistent and oppressive heat across the entire planet. There are no seasons as we know them on Earth. Venus experiences a stable climate devoid of the fluctuations that characterize our own world. The surface of Venus is a fascinating and diverse landscape, sculpted by volcanic activity and various geological processes. Large volcanic structures, such as Mont Mons and Sif Mons, dominate the terrain, showcasing the planet's potential for active volcanism. Mont Mons, one of the tallest volcanoes, rises approximately 8 miles, 13 kilometers, high, dwarfing Earth's Mount Everest. Venus's geological features indicate a dynamic history of volcanic activity. The extensive lava plains, marked by lava flows and unique geological formations, suggest that the planet has undergone significant resurfacing events. Scientists theorize that Venus may experience periodic volcanic eruptions that cover older terrain with fresh lava, a process that continually reshapes the landscape. The presence of features known as coronae, large, circular structures caused by the upwelling of magma, further supports the idea of an active geological past. These coronae are formed through complex processes involving heat, pressure, and tectonic activity, reflecting the intricate geological dynamics at play on the planet. One of the most intriguing aspects of Venus is its potential history of water. Geological evidence suggests that billions of years ago, Venus may have harbored vast oceans of liquid water, creating an environment that could have supported life. The transition to its current state is a mystery that has puzzled scientists for decades. As conditions on the planet changed, the thickening atmosphere likely led to a runaway greenhouse effect, causing any existing water to evaporate and escape into space. Understanding the isotopic ratios of hydrogen and deuterium in Venus's atmosphere provides crucial insights into this dramatic transformation. The depletion of water vapor compared to Earth's atmosphere suggests that Venus has lost a significant amount of water over time, raising questions about its past and what processes may have led to such a change. Research into Venus's geological features, including potential ancient riverbeds and signs of past volcanic activity, continues to inform our understanding of its climate history and the possibility that it once had conditions conducive to life. Venus has long captured the attention of scientists and space agencies alike. The Soviet Union's Venera program, which began in the 1960s, was a pioneering effort that successfully sent multiple probes to the surface of Venus. These missions provided invaluable data, revealing a landscape dominated by volcanic plains, impact craters, and unusual geological formations. Despite the probe's limited operational lifetimes due to the extreme conditions, NASA's Magellan mission in the early 1990s employed radar technology to map nearly 98% of Venus's surface, uncovering its geological features in remarkable detail. However, even with these advancements, many questions remain about the planet's atmosphere, surface processes, and potential for past habitability. As technology evolves, new missions are on the horizon. NASA's upcoming Da Vinci Plus mission aims to analyze the composition of Venus's atmosphere and study its geological history. The mission will focus on understanding the planet's atmospheric dynamics, including its clouds and potential chemical processes, which may offer insights into why Venus diverged so dramatically from Earth. Simultaneously, the Veritas mission will utilize advanced radar imaging to create high-resolution maps of the surface, seeking clues about past water presence and ongoing geological activity. These missions hold the promise of answering fundamental questions about Venus's past and its role within the broader context of planetary science, shedding light on the evolution of terrestrial planets in our solar system. The study of Venus is not merely an exploration of one planet. It is a gateway to understanding the evolution of all terrestrial planets, including Earth. By comparing the geological, atmospheric, and climatic histories of Venus and Earth, scientists gain insights into the processes that can lead to diverse planetary environments. Investigating Venus's extreme conditions also has implications for the search for life elsewhere in the universe. Understanding how a planet can evolve from potentially habitable to hostile conditions informs our search for exoplanets with similar characteristics. The lessons learned from Venus may help refine our criteria for identifying potentially habitable worlds beyond our solar system. Moreover, the challenges faced in exploring Venus inspire advancements in technology and engineering. Developing robust instruments capable of withstanding extreme temperatures and pressures opens new avenues for exploration, potentially enabling future missions to other inhospitable environments, such as the atmospheres of gas giants or the surfaces of icy moons. In summary, Venus serves as a striking reminder of the diversity of planetary environments within our solar system. While it shares many similarities with Earth, its harsh climate and complex geological history illustrate the extremes of planetary evolution. The story of Venus is not just about a planet. It is about the evolution of worlds, the delicate balance of conditions that can foster life, and the forces that can lead to its demise. As we continue to study this captivating world, we uncover not just the secrets of Venus, but also gain a deeper understanding of the delicate balance required for life as we know it. The ongoing exploration of Venus not only enriches our knowledge of our neighboring planet, but also enhances our understanding of Earth and the broader cosmos. So, as we gaze up at the evening sky and spot Venus shining brightly, a beacon of curiosity and wonder, let us remember the stories it holds. Tales of fiery volcanoes, relentless heat, and the insatiable quest for knowledge that drives humanity to explore the mysteries of the universe.